We all take a lot of pictures every day, capturing events that are dear to our heart. And while taking pictures is fun, viewing them as static flat images could be more exciting at times. What if we could breathe new life into these pictures, ultimately helping us cherish and celebrate past moments? Scanning and zooming a virtual camera is a common approach to animate still images, which is typically referred to as the Ken Burns effect. However, the resulting video lacks motion parallax and hence provides a limited perception of depth. We extend this approach to the third dimension and introduce a technology to synthesize the 3D Ken Burns effect from a single image. This technology allows us to automatically animate otherwise still images in a three-dimensional manner. Like with the common 2D Ken Burns effect, our virtual camera fly-through is parameterized by a source and target cropping window. As such, our technology also allows users to intuitively adjust the result to their liking. Our system is robust and works on a wide variety of image content. Furthermore, its interface allows users who prefer to manually interact with it to generate compelling results with little to no practice. To synthesize the 3D Ken Burns effect, our method first estimates the depth of the input image before employing novel view synthesis to generate the output video. While recent methods for monocular depth estimation have shown good performance in public benchmarks, we have identified major issues when using them to produce high-quality view synthesis results. First, geometric relations, such as planarity, may not be captured sufficiently well. As such, geometric distortions like bending planes often appear in the synthesis result. Notice that the depth from off-the-shelf depth prediction methods lead to the white building leaning to the left and right. Second, semantics of objects may not be taken into account. In many cases, this leads to an inconsistent depth estimate within the same object which, for example, leads to objects being torn apart. Notice that the depth from off-the-shelf depth prediction methods lead to the hand of the boy being separated from the rest of the body. Third, inaccurate depth boundaries will lead to artifacts in the novel view rendering. Current state-of-the-art methods for single-image depth estimation often estimate the depth at a coarse scale and then utilize bilinear interpolation to obtain the full resolution prediction. As such, they are inherently prone to inaccurate depth boundaries. In this paper, we design a semantic-aware depth estimation dedicated to addressing these issues. To do so, we separate the depth estimation into 3 steps. We first estimate the coarse depth and facilitate a geometrically sound depth prediction by forcing the utilized neural network to primarily rely on deep image features. Notice the inconsistent depth within the red car and the inaccurate depth at object boundaries like at the clock tower. We then address semantically inconsistent depth estimates, such as within the red car in the given example. Specifically, we refine the depth via instance-level segmentation masks to ensure that the depth within salient objects is consistent. Lastly, we leverage a depth refinement network that is trained to upsample the coarse depth estimate. In doing so, it is guided by the high-resolution input image and is supervised to account for inaccurate depth boundaries. To synthesize the 3D Ken Burns effect from the estimated depth, our method first maps the input image to points in a point cloud, through which null view renderings can easily be obtained. However, the point cloud is only a partial view of the world geometry as seen from the input image. The resulting novel view renderings are thus incomplete due to this occlusion. One possible solution to this issue is to utilize off-the-shelf image inpainting methods to fill in the missing areas in each synthesized view frame. However, existing inpainting methods do not explicitly reason about geometry and thus may not clearly separate foreground objects from the background. Furthermore, this pair frame inpainting approach is temporally unstable and does not allow for a real-time application as required when manually interacting with our user interface as shown at the beginning of this demo. In this paper, we design a dedicated view synthesis pipeline to address these issues. Given a point cloud obtained from the input image and the estimated depth, we perform joint color and depth inpainting to fill in missing areas in incomplete novel view renderings. The inpainted depth can then be used to map the inpainted color to new points in the existing point cloud. Extending the point cloud addresses the problem of disocclusion, while the point cloud rendering preserves temporal consistency and can be done in real time. We evaluated several datasets that provide ground truth depth information to supervise the training of our depth estimation pipeline, including NYU-V2 as well as megadepth. However, these datasets only provide sparse annotations that are subject to inaccurate depth boundaries. We thus created our own computer-generated dataset from photorealistic virtual environments. This approach not only provides us with accurate depth information, we are also able to extend it to a multi-view dataset in order to supervise the training of our color and depth in painting network. We conduct an informal user study to evaluate our system in supporting the 3D Ken Burns effect. Specifically, we ask participants to use our system as well as 2 commercial tools and find that our system enables users to achieve good results while requiring little effort. We investigate the effectiveness of our method in automatically synthesizing the 3D Ken Burns effect. To do so, we compare our 3D result with a 2D baseline in a subjective user study. We find that users have a strong preference for the 3D Ken Burns results of our system. We evaluate the effectiveness of our depth prediction model on the NYU-V2 as well as the IBIMS-1 benchmark and note that our method compares favorably to state-of-the-art depth prediction methods in all depth quality metrics that we analyzed. Please kindly refer to our paper for a high-resolution version of this table. We also note that our depth estimation network better preserves the scene structure, as shown in these depth-based scene renderings. Our depth estimation network is even able to preserve the scene structure of relatively complex scenes, as in this example of an alley. Lastly, we conduct an additional subjective evaluation and compare the 3D Ken Burns results from our system with those from professional artists. We find that the participants of an informal user study did not have a strong preference, demonstrating the effectiveness of our approach. We subsequently show more video results. Please note that the shown examples were automatically generated without any user feedback. While our method can generate a plausible 3D Ken Burns effect for images of different scene types, the results are not always perfect. We subsequently show a few examples with failure cases. Please see our paper for more details. Thank you very much for your time.